Section 8.9 is going to discuss variational problems. These are going to be probably the most gentle word problems that you will see in this course, and they all kind of follow a similar pattern. There's a lot of phrases in the English language that actually correspond to things in math. So the first part of what we're going to do is we're going to try and understand these phrases and what they mean. So there's a couple ways to express some direct variation. That is, y varies directly with x, or y is directly proportional to x. So these two refer to a mathematical equation like this. Y equals kx. So y is your variable, x is a variable, k is some constant of proportionality. And during the process of solving the problems, we're going to have to figure out what k is, but they're going to give you some information that'll help us solve for k. Likewise, there's a couple other things we can say. Y varies inversely as x, or y is inversely proportional to x. And that's going to refer to a model like this, where y is some constant divided by x. And the important thing to see here is that x is in the denominator. Lastly, y varies jointly with x and z. So that's this one. And that reflects a model with more than one variable. But even though it has more than one variable, it still has just one constant. So a couple quick examples. C varies jointly with x, y, and z. So C is going to be by itself on the left-hand side of your equation. And on the right-hand side, you're going to have the product of x, y, and z and just one constant. All these problems are going to get just one constant. R varies directly with the square of s. Well, the square of s can be written as s squared. If it varies directly, then it's just going to be k times that. So k times s squared. Or if you have something that varies inversely with the cube of t, because it varies inversely, that puts that cube of t in the denominator. You'll have your k in the numerator. So those are a couple quick examples. This kind of stuff comes up more often than you might think. Let's see if I've got, I don't have the article that I used to, but there's a lot of places where you see direct variation applied to, like, your metabolic rate is directly proportional to your mass, to some 1/4 power, the spacing of trees in a forest, the length of lifespans are going to be based on metabolic rate, etc. But let's start pretty slowly. Our first job is going to be to try and figure out the models that correspond with these statements. So here's problem number 20 for you. V varies inversely as the square of s. Let's see if we can't write that as one of these models. So that's going to be this one right here. Varies inversely, or is inversely proportional to. That's going to put that term in the denominator. Anyone want to be brave on this first one? What would this model look like? What equation would I get? Thank you. A lot of voices on that one. Appreciate it. V equals k over s squared. And guess what?
That was easy.
We're done. That's all I have to do on that one. Just write down a little bit of a mathematical model. So let's try another one. D varies jointly as r and t. So that's going back to examples like these two. D varies jointly as r and t. Someone else. I haven't picked on you yet today. Perfect. D equals k r t. The only time something goes in the denominator is if it varies inversely. So varies jointly or is directly proportional to, etc. All those terms are going to be in the numerator. Well done. Thank you. The last one here kind of mixes things up. M varies inversely as the cube of n, and jointly as the square, or as x and the square of z. So we'll start out with an m on the left-hand side equals k. Varies inversely as the cube of n. What's that mean about the cube of n? Where am I going to find that in my expression? In the denominator. So n cubed, and jointly as x and the square of z. So what's that numerator going to look like? Good. Z is squared and x isn't. So k times xz squared over n cubed. You could also write that as kxz squared over n cubed like that. Either way is fine. The important thing is that you have just one k. There's only one constant for this. And that your model puts the n cubed in the denominator and the x and the z squared in the numerator. Well, it's by itself here because I'm kind of writing it out in front. But over here, it's part of the numerator. Neither, whatever you like, whatever you're more comfortable with. And to see and understand the equivalence between these two, you can think of this as being k over 1. And then just multiply the fractions together, like that. Okay. So, let's see here. Let's go out online for a second. And has anyone ever seen something in Chicago on the John Hancock building called the Tilt? It's pretty cool. Way up at the top, they have this little thing here where they'll lean you out and you look straight down to the street, and it's about 1,000 feet straight down. Straight drop. So, did they? One of the panes cracked? Well, while I was doing it, the operator has a sense of humor. He leans you out, first of all, 15 degrees, and then 20, and then 30 or so. And on the last one, he goes, "Oh, you guys are a lucky group. We're going to open the windows today." At which point, and you realize, okay, you got a good sense of humor. But it's kind of a nice ways down. So let's see. That's what it'll look like. So you're looking straight down, about 1,000 feet. So we'll keep that one in mind while we look at our problem. An object in free fall travels a distance s that is directly proportional to the square of time. So let's stop right there, because that gives us enough information to write down a little bit of a mathematical model. The distance s is directly proportional to the square of time. So, Mackenzie, what could I write there? What model would that give me? S is directly proportional to the square of time. All right, square of time. There's something I'm missing here, though. Good, the k. So that k is what we're going to have to determine next. But the first step in these is to figure out your model. So s equals kt squared. The second step, they're going to give you some information that's going to allow us to solve for k. So it says, if an object falls 1,024 feet in 8 seconds, stop the presses. Let's see what they're giving us here and see if that doesn't allow us to solve for k. Object falls 1,024 feet in 8 seconds. If I was to put those terms into the model, what goes where? Yeah, feet goes where s is. 1,024 equals k times 8 squared. 8 squared is 64. So we get 1,024 equals 64k. Divide both sides by 64, and I get 16 for k. Great. So that's the second step here. Let's take a look at the third one. Well, for the third one, I know what k is. So k is 16. So let me put that in my model. Instead of s equals kt squared, it's now s equals 16t squared. The last part of this is how long will it take to fall 4,096 feet? So I'm not going to take the time to show it here, but there's a thing called the Grand Canyon Skywalk, which is kind of like analogous to the tilt. Yeah, and it's probably close to a vertical mile to the river from the south rim. Any case, where's that 4,096 feet go? S. 4,096 equals 16t squared. Suggestions to solve for t. Perfect. So that would give me 256 equals t squared. Take the square root on both sides. Perfect. So I get 16 equals t. What units would go with the 16? 16 seconds. Yes. So kind of a long fall. I divided by 16 here, and then took the square root on both sides here. Technically, there's a plus or minus square root, but I'm not going to worry about a negative 16 seconds. I'm only going to worry about the positive 16 seconds. So, square root of 256 is 16. Just take 256 and hit the square root button. So, square root of 256, 16. If you type in the 256, I'll kind of show you a little trick, then we'll understand it later. If you raise it to the 0.5 power, that's also like taking a square root. That's what I usually do. I don't know why. It's just easier for me. It's just, I don't know. We'll understand that when we do Chapter 9. I think that's where it comes up. Let's try another one like that. Kind of the same pattern here. Problem number 38. Suppose the distance that a vehicle travels after brakes have been applied varies directly as the square of the speed at which it was traveling. So, in this one, they kind of leave it up to you to figure out what variable names you're going to use. I would suggest that when you're doing these things, you give yourself some variable names that reflect the problem, like d for distance. So the distance that a vehicle travels after its brakes have been applied varies directly with the square of the speed. Suggestions there? S. So let's stop there. This gives us enough information to write down a relationship between these two variables. Emily, not sure I picked on you yet today. So what could I write down as a relationship between these two? Yeah, good. D equals s squared, and then we need that k in there as well. So d equals ks squared. Good. Thank you. So that's the first step. The second step says if the stopping distance for such a vehicle going 24 miles per hour is 24 feet, let's stop here. This is going to allow me to solve for k. I just got to be careful about what I put in where. So where's the 20 go? S. And then the 24 would be over here. So that's 24 equals 400 times k. 0.06. Good. So you divide both sides by 400 and we get k equals 0.06. Thank you. let's put that into our model. Our model is now very specific to this problem. Distance equals 0.06 times s squared. I didn't need to write that in parentheses, my bad. But now we're ready to answer the last part of this. And what you should see here in these first two examples is kind of a nice pattern. Figure out the model, determine k, and then answer one last question. What is the stopping distance for a vehicle traveling 50 miles per hour? Well, where do I put in the 50? S. So it's going to be 0.06 times 50 squared. 50 squared is 2,500 times 0.06 is going to be 150. What do you think the units are going to be? Feet. What's surprising is that that distance does a lot more than just double, even though we've done a little bit more than double the speed. So the reason for that is because it's not a linear relationship. It goes up with the squared. So, okay, let's stop things here. Let me give you a few homework problems to look at. We'll do a couple more problems from the section maybe on Wednesday. For homework for now, try 17 through 23 and 35 through 41. So 17 through 23 and 35 through 41.